Fine. Right. So we are on. Where are we? Page 12. Sort of. I'm doing it in a slightly different order from the top. I mean, we're definitely on page 12, right? But, okay. One of the advantages of doing organic chemistry is you kind of do everything twice. So when we're talking about haloalkanes, we talk about how they can react with ammonia to make amines. And then when we talk about amines, we talk about how we can make them from haloalkanes with ammonia. So, bit of reinforcement there. So we all remember nucleophilic substitution reaction mechanism, right? If you don't happen to have page 12 open, maybe just see if you can remember how that goes. Or you can just cheat and look at page 12. Well, not cheat. Refer to the source. Okay, let's run through this. So, lone pair on the nitrogen kicks us off, attacks the carbon because it's delta positive, because of the electron withdrawing bromine next door, and then the bromine leaves, making a space for the nitrogen to come in, but we're not finished yet because nitrogen had 3 bonds, had plenty of bonds, and it's got 4. It's given up some of its own electrons, so it's got a positive charge, and we need to give nitrogen back its electrons, so we take them from a nitrogen-hydrogen bond. Sometimes in the textbooks you'll see an additional ammonia kind of picking off that hydrogen there, which is all fine, but it's not an AQA marking point. So if it's not in your answer, you'll still get full marks. Okay. That's our first method. Second method is reduction, or hydrogenation would be another name for this type of reaction. Hydrogenation is just a nice, quite descriptive term. It just means adding lots of hydrogen to things. We can hydrogenate carbon-carbon double bonds, for example, We can also hydrogenate the triple bond that is the nitrile which we do with hydrogen and a nickel catalyst and high temperature and pressure. Yeah. And that all that does really is put lots of hydrogens on the molecule there. I'll just compare these two methods just for a moment. We get rid of that bit there. CH3, CH2 and H2. Look at the two products. What do we notice? The same. Okay. So we've got two different routes to the same thing here, but the different routes do something, well, different. Because I could make this from a haloalkane, couldn't I? I could make my nitrile from a haloalkane. But what haloalkane would I start with to make that nitrile? No. Come on, Jason.
I was going to say methane.
Well, methane's not very good at reacting because there's only functional groups. So just put a functional group in there for me. Chloromethane. Okay. So that's a straight substitution reaction there, followed by the hydrogenation. What we notice is this route here starts off with 2 carbons. We're changing the functional group, but we end up with 2 carbons. Whereas this route here, start off with 1 carbon, then we add the nitrile, and then magically we've added another carbon. So the nitrile is not just another thing we can swap on, swap off. It's a functional group which does a very rare thing, which is to extend the length of the carbon chain. There's really no other functional group that I can just swap a halogen for, and then magically we've got a longer chain there. Okay, so just make a note somewhere. Nitriles can extend the carbon chain. Okay. There's also an alternative method there. I've just put in the question, put in the book even, which is lithium aluminium hydride, as we used to call it, followed by dilute acid. But you only need to learn one method, and LiAlH4 is off the syllabus, so they won't give that. They won't suggest that to you as a AQA won't put it in a reaction equation. Does that make sense? I'm not sure that made sense. Right, last one. Reduction of a nitro group. A nitro group, I'm just going to put this over here, is that all right? So I'm kind of running out of space. Nitro group is, we learned about it recently, the NO2 group that sits comfortably on benzene rings. And we can reduce that or hydrogenate that to make NH2. The reducing agent we use is tin and HCl, which might sound a bit odd. Tin and HCl. But what happens if you add tin to HCl? And hydrogen makes hydrogen, metal and acid, right? So it's a way of just generating some hydrogen. It's basically a hydrogen generator right there in the reaction mixture. You're making fresh hydrogen for the NO2 to react with. We're going to actually try and balance this equation. We're going to sort of balance it in a very unusual way because you're not required to write balanced redox reactions for organic molecules. By balanced redox reactions, I mean with electrons. So if you were writing some sort of oxidation reaction, say, oh, hello, CHO, you could balance that with electrons. You might want to have a go. It will be a complete waste of your time because it's not on the syllabus, but it will work. You can balance that equation with electrons in exactly the same way as we would balance, I don't know, dichromate, say, or whatever else it is that we did in topic 7 last year. You know, H balances with H plus and O balances with water, and you check the charges and all of that malarkey. You can do that, but you don't have to. So we have a slightly simpler method for doing redox equations in organic chemistry, and that's that I just say, okay, I'm just going to add some H. There we are. H in square brackets just means some hydrogen from a source. I'm not going to worry too much about the form of that hydrogen. Is it H plus? Is it H minus? I don't care. But we're still going to kind of balance the equation. So those oxygens are going to have to go somewhere. I have to keep track of them. So what do we think they would make on the right hand side? Balance oxygens with water. Oh, there's 2 NO2, so I'll need 2 of them. Sorry, I'm squashing up a little bit here. Okay, so number of hydrogens that I actually need. Well, I've got 2 there and 4 there, so I'll need 6 of those. So that kind of counts as a balanced equation for the hydrogenation of NO2. Okay, that's all I want to do right now.